So, welcome back. In the last two sessions or two videos, we were discussing Born Oppenheimer Approximation. Today, we are coming to the final video of this one. I hope I can finish it in next to 40 minutes. The discussion on Born Oppenheimer Approximation. You may be remembering that we start and where how we reached so far. And we started from constructing the Hamiltonian for a system of p electrons and n nuclei. This one, right? This one. This is where we started. We constructed the Hamiltonian for p nuclei and this one, p nuclei and n electrons, p electrons and n nuclei. Then we were then we have reached here. We have reached here. See, we have constructed an equation like this: sigma I is equal to 1 to n h square divided by 8 pi square capital M I del I square psi n r divided by psi n r plus et is equal to minus sigma j is equal to 1 to n h square divided by 8 pi square m del j square psi electronic rr divided by psi electronic rr plus u plus vrr is equal to a constant u. Okay, that's what we have done so far. So in the last class itself I said that now we can equate both hand sides of this equation with the u. So let us start making the two equations from here. So the first equation is that I will take this part, okay, this part, this one. Okay, so let me take this to the other side, because this is plus h square divided by 8 pi square m I del I square psi n r, like that. For me, it would be better if I have negative sign here, because the kinetic energy part of the Hamiltonian is minus h square divided by 8 pi square mi and so on, right? So I will take this to the other side. So the equation will be like minus sigma I is equal to 1 to n h square divided by 8 pi square mi, this is capital Mi, del I square psi n r divided by psi n r plus u this, because I have taken that to the other side. Okay, that is equal to plus u is equal to et. Okay, this is the first equation. So let me call I will give the number to the next equation. So this is the first equation. What I have done here is that I have equated the left hand side of this equation to u. Then I have taken one term to the other side. That's why this became minus plus u is equal to et. Okay, so let me multiply this equation, the entire terms in this equation, with the psi n r. Then I will get minus sigma I is equal to 1 to n h square divided by 8 pi square mi del I square psi n r plus u into psi n r is equal to et psi n r. Okay, this is the equation that I am getting, and let me call this as equation number 10. Okay, here you can see that this equation is like this is the first term in this equation, that is the first operator in this equation, that is minus sigma I is equal to 1 to n h square divided by 8 pi square mi del I square. What is that? That is the kinetic energy operator for the nucleus, right? We already know this. This is the kinetic energy operator for the nucleus, T n cap, plus U psi n r, we can write like this, psi n r is equal to Et psi n r. We can write like this. So this is a Schrodinger wave equation, and this Schrodinger wave equation is for the nuclear wave function psi n r, right? This is a Schrodinger wave equation for nuclear wave function psi n r. So this is Schrodinger wave equation for, or Schrodinger wave equation with a nuclear wave function psi n r. Okay, this is a Schrodinger wave equation with a nuclear wave function psi n r. So here we can examine this Schrodinger wave equation. You can see that there is a kinetic energy part and there is a U. Okay, so kinetic energy part plus U psi n r is equal to energy into psi n r. That is an eigenvalue equation and Schrodinger wave equation, and therefore here U represents the potential energy for the nucleus. So this one represents the potential energy operator for the nucleus. Potential energy operator for nucleus. Okay, so we can write it like H cap n. Therefore, H cap n, or Hamiltonian for the nucleus, H cap n is equal to kinetic energy part of the Hamiltonian plus the potential energy part U. Okay, kinetic energy part plus potential part U. That is a nuclear Hamiltonian. Okay. Similarly, again what we can do is that we take our equation. We take the equation number 9 and equate this, the right hand side of this equation number 9 with U, right? So we get minus sigma j is equal to 1 to n. Okay, minus sigma j is equal to it is not 1 to n, it is 1 to p. It was a mistake. J is equal to 1 to p. Okay, because this is the number of nucleus. P number of nuclei are there. So that is, we can write it like minus sigma j is equal to 1 to p. Okay, h square divided by 8 pi square m del j square, right? Del j square. What was that equation? Let me check it up. Del j square psi electronic RR divided by psi electronic RR. Then what was remaining there in that equation? That is equal to plus V RR is equal to U. That is equal to U. So again I can multiply these entire terms in this equation with the psi electronic RR. Then I will get minus sigma j is equal to 1 to p h square divided by 8 pi square m del j square psi electronic RR plus VRR psi electronic RR is equal to U into psi electronic RR, right? That is what I am getting. Okay, so you know this is from here. Okay, this was made from here, this part. Okay, now we have this equation, and this equation also you can check this equation. It is also a Schrodinger wave equation. You can write this as minus sigma j is equal to 1 to p h square divided by 8 pi square and del j square. That is the kinetic energy operator for the electron, right? We already know this. So kinetic energy operator for the electron. T cap electronic plus what is the other operator? VRR. This is not U, V. Okay, VRR. Then this two operators operates over the function psi electronic R is equal to U into psi electronic R, right? So this equation is the Schrodinger wave equation with the electronic wave function. So this is the Schrodinger wave equation with the electronic wave function. Electronic wave function. Electronic wave function. Okay. So we have two equations now. One was the Schrodinger wave equation with the nuclear wave function psi and r, this one, and again we have another equation. Now this is the Schrodinger wave equation with the electronic wave function. Electronic wave function is psi electronic r, right? This is Schrodinger wave equation with the electronic wave function. So we have two equations now. Okay, again we can do some simplifications. You already know that this is T electronic plus VRR, T electronic plus VRR is equal to, we have already done this, T electronic plus VRR is equal to, let me check where we have done this, T electronic plus VRR, we have done this in the first session. Somewhere we simplified this. Yeah, it is here. So you look at here. This one. Okay, here. T electronic VRR is equal to this one. Four terms together. And then we wrote it like T electronic VRR is equal to H cap electronic RR plus VRR. This part, right? So we can write it T electronic RR is equal to H cap electronic RR plus VNNR. So I write like that. So let me write T electronic plus VRR is equal to H cap electronic RR, H cap electronic RR plus VNNR, right? VNNR. Therefore, we can write again the Schrodinger wave equation for the electronic wave function. We can write it like instead of T electronic plus VRR, we can write H cap electronic RR plus VNNR psi electronic RR is equal to U into psi electronic R. Okay, we can write like that. Let me give some numbers for these equations. Okay, so where did we give the numbers? So this was equation number 10, and let me write this as equation number 11, and I will give this as equation number 12. Okay, so equation number 12. So equation number 12 is H cap electronic RR plus VNNR psi electronic RR is equal to U into psi electronic RR. So let us examine this equation number 12. Okay, let us examine a little bit detail of this equation number 12. Okay, and now we already know that the omission of a constant C from the Hamiltonian does not affect the wave function. Did you understand anything what I said? The omission of a constant c from the Hamiltonian does not affect the wave function. Rather, it decreases the energy eigenvalue by c. For example, you have a Hamiltonian. Let me write it in the side. You have a Hamiltonian here. I write it in another color. You have a Hamiltonian here, Hamiltonian, plus c psi is equal to E psi. Okay, this is your equation. And this can be proved that if you are omit this C from this Hamiltonian, you are omitting this C from the Hamiltonian. Also, omission of that constant C from the Hamiltonian, it will not affect the wave function. Rather, it will affect the energy eigenvalue E only. How it will affect the energy eigenvalue E will be decreased by a value C. Means if you are constituting another equation without C, that is h cap psi, it will be equal to E minus C into psi. Okay, so if you are constituting h cap psi, then h cap psi will be equal to E minus C into psi. So what is the meaning of that? Omission of a constant from the Hamiltonian does not affect the wave function. Rather, it will affect the energy eigenvalue only. It means that if you are solving these two equations, okay, this equation and this equations, in both cases you will get the same eigenfunction. Eigenfunction is not going to change. Only thing is that the eigenvalue will change. In the first case, E will be the eigenvalue. In the second case, E minus C will be the eigenvalue. In the second case, the eigenvalue is E minus C because you have omitted the constant C from the Hamiltonian in the first equation. Okay, so that is why you have this kind of results. So we can apply the same theorem here also. Here we have h cap electronic plus Vnn. So if you are omitting Vnn from this equation, what will be the resulting equation? The resulting equation will be, I will write it in the yellow. Then the resulting equation will be h cap electronic RR. We have omitted Vnn. Then what is remaining is psi electronic RR, h cap electronic RR, psi electronic RR will be equal to what will be the result? Then the eigenvalue, here the eigenvalue is u, and that u will be reduced by from u Vnn will be reduced. In the new eigenvalue will be u minus v n psi electronic RR. In both cases, the wave function is same. Okay, so we can see that we can write it in another way. So h cap electronic RR psi electronic RR. Okay, that will be equal to, since it is purely in terms of electronic wave function. Okay, here we have the Hamiltonian for the electron. So let me write it as E electronic psi electronic RR. So E electronic is the new eigenvalue obtained by omitting Vnn from h cap electronic RR. Okay, so from the first equation we are omitting Vnn, and then we are getting another Schrodinger equation. In that Schrodinger equation, E electronic is the eigenvalue. So from our theorem, this theorem, we know that E electronic will be equal to U minus Vn. That's what we know, U minus Vn. Or in other words, we can write U is equal to E electronic plus Vn. Okay, we can write like that. So what does it mean? It means that instead of solving equation number 12, you can solve equation number 30. Okay, equation number 13. And once solving equation number 13, you will get E electronic. By solving equation number 13, you will get E electronic. That is the energy eigenvalue of equation number 13. Then you can add Vnn to this E electronic. So when you are adding Vnn to E electronic, you will get U, right? So instead of getting the value of U by solving this big equation, you can solve this big equation 12. You can solve the shorter equation, equation number 13, and add Vnn to the E electronic, the energy eigenvalue of the equation number 13. Then you will get the value of U. Okay, that's what we can understand from here. Now, let us examine this equation further. We have this equation H cap electronic Vnn. I will write it shortly. H cap electronic Vnn. H cap, sorry, let me choose another color. H cap electronic. H cap electronic plus Vnn. Vnn. Xi electronic. Xi electronic. You already know H cap electronic RR, Vnn R, psi electronic RR is equal to U psi electronic. Okay, this is our equation, U psi electronic. And then what is this U actually in this equation? In this equation, U is equal to E electronic plus Vnn. It means that U is equal to electronic energy including the internuclear repulsion, because Vnn is the internuclear repulsive potential energy. Therefore, U is equal to electronic energy including internuclear repulsion. Okay, so that's the electronic energy including internuclear repulsion. Now what we have to understand here is that it is important that you understand what is Vnn. You already know what is Vnn. What is that Vnn? That is the potential energy due to nuclear repulsion, right? In other words, we can write it like Vnn is equal to sigma. You know this, sigma k less than L. We already wrote it, k less than L, and then Zk ZL E square divided by RKL. I hope you remember this. Here Zk is the atomic number of the kth nucleus. ZL is the atomic number of the lth nucleus. E is the elementary charge of the electron or proton. Capital RKL is the distance between the nucleus K and the nucleus L, right? So this is the internuclear repulsive potential energy. Okay, internuclear repulsive potential energy. Okay, and what we have to understand is that, let us check this equation. This is the equation for, what was this equation? The number of this equation, that is H cap electronic Vnn, that is equation number 12. Okay, so if we are checking this equation number 12, we have Vnn here, where Vnn is this one, and Vnn depends upon the internuclear distance RKL. But we have to understand that when we are solving this equation number 12, the internuclear distance RKL are not variables. That's very important. Okay, so this RKL, internuclear distance, that is the distance between the kth nucleus and lth nucleus, this is not a variable. Not a variable when we are solving this Schrodinger wave equation. It is not a variable. It means that it is fixed. The nuclei are fixed at some constant value, right? Nuclei are fixed at constant positions. Nuclei are fixed at constant positions. But we know that Nuclei are not fixed at constant positions, but there are infinite number of different nuclear configurations corresponding to different nuclear positions. We know this fact. But when we are solving this Schrodinger verification, we fix the nuclei at a certain constant positions. Okay, we will fix the nuclei at a certain constant position. Then we go for solving this Schrodinger verification. And when we are solving the Schrodinger verification, we will get the psi electronic and U. Okay, and when we are getting the U value, U is the electronic energy including the internuclear repulsion. You are getting the U value. And when you are getting the U value, for example, you get a short U value which is called as U1. And U1 corresponds to a particular nuclear position. Okay, because you fixed the nucleus at a certain position, then only you solve this Schrodinger verification. Therefore, you got a U value which is equal to U1, and U1 corresponds to the configuration 1. Configuration 1 of nuclei means nuclei are fixed at a certain configuration. That configuration is named as configuration 1, and for that particular configuration only you are getting the energy eigenvalue U1. Now what we are doing is that we are again changing the configuration of the nucleus, means you are going to change the RKL value. You are going to change the RKL value and keep that RKL value fixed. So you fixed a value, RKL value in the beginning, then you solve the Schrodinger verification. During the Schrodinger, when you are solving the Schrodinger verification, you did not consider RKL as a variable, rather you consider RKL as a fixed value. That's okay, you solve that Schrodinger verification. Again, you are changing the RKL value, keeping another configuration, means for configuration 2, you are changing the RKL value. Once you fixed the RKL value for the configuration 2, it's not a variable because it is fixed again to another value, right? Then you are solving the Schrodinger verification again. Then after solving the Schrodinger verification, you will get a U value which is equal to U2, and U2 corresponds to the configuration 2 of nuclei. Configuration 2 of nuclei. So what we can do? We know that there are infinite number of nuclear configurations like that. You can choose any value for the RKL, right? You can choose infinite number of configurations, and for this infinite number of configurations you are finding out the U values. Okay, and so for different configurations you are finding out the U values. That is what you are doing here. And let us examine what will happen if we are doing this for a diatomic molecule. Diatomic molecule means a molecule having two atoms. Two atoms are connected by a bond. Okay, and you are doing this procedure for a diatomic molecule. Atom A is connected to atom B. Okay, and you have only one RKL value here because you have only two nuclei. Therefore, the distance between the nucleus A and the nucleus B is R. So you are going to solve the Schrodinger verification 2, so Schrodinger verification 12, that is electronic Schrodinger verification for this system. Then you are fixing the R value at a certain distance. For example, you are fixing R value at 0.5 angstrom. Okay, then you solve the Schrodinger verification. Okay, then you will get a particular U value. Then you change the R value to 0.6 angstrom. Then you find the U value. Then you again change the R value and fix the R value to 0.7 angstrom, like that. So you are going over a range of R values, and for each R value, keeping that R value as fixed, then you solve the Schrodinger verification and find out the corresponding U values. Okay, so corresponding to different R values, you can find out the U values. Then you are going to plot the U value against R. So let me take U in the Y direction. Okay, I am taking U in this Y direction. This is the y direction. I am taking u here, and then I am going to take the r in the x direction, So here I have a r, okay. So for different r's, I am finding out u, and then I am going to plot. So if I am choosing r as 0, means there is no distance between a and b. What will be the value of u? What will be the value of u? If I am choosing the r value as 0, you can guess what will be the value of u. What will be the value of u? Because you already know that u is equal to E electronic plus Vnn. You know this, right? U is equal to E electronic plus Vnn. So whatever may be the value of V electronic, we don't know. But we know what is the value of Vnn. Because Vnn has r in the denominator. If this is Vnn, r in the denominator. So if r, since r is in the denominator, if the value of r is equal to 0, then the value of Vnn is infinity, right? So E electronic plus infinity is also infinity. Therefore, u will be infinity. Therefore, when the two atoms are very, very close, or the two atoms are touching each other at that point, when r is 0, at that point, the u will be infinity. Therefore, you should be very careful when you are drawing this. So since u is infinity, you should draw like this. Okay, you should not touch this curve in the u axis. Sorry, my drawing is very poor. Okay, some of you may be very good artists, and you will laugh what I am doing. And I am drawing carefully. Okay, so this is how. When the r is increasing, then the u at the beginning was infinity. That is why I did not touch this curve at the u axis. Once you touch the curve at the u axis, that it means that it has some fixed value. Okay, it has some finite value. Therefore, you should not touch this curve at the u axis. That's a mistake. Many people, and even in some many textbooks, this curve touches the u-axis. It should not touch. It touch means it touches some finite value. That is not correct. So you should not touch this there. It means that it is exponentially increasing to the infinity. Okay, it's like an exponential increase. Then it is going to infinity when the two atoms are coming close. And when the atoms distance are increasing, then that u value will decrease. The u value will decrease, and then it reach some point here. And when you are again increasing the r, value, then what you can see is that the u value will increase. Okay, and u value will increase, and then you are reaching at a certain value of r. When you are reaching that value of r, that distance between the two atoms are not enough to keep any internuclear interaction. Okay, you have reached a long r value, okay, you have reached a big r value, so that the internuclear distance is too long, and that distance is not enough to keep the bond between the two atoms, so that at that distance the bond breaks. Once the bond breaks, we have only atomic constituents. We have the atoms A and atom B, and these two atoms are independent atoms. Okay, so once they are independent, the U will be the sum of the atomic energies. Atomic energy means the energy of the atomic systems. Okay, the system A and system B, they are not connected to each other. There is no interaction between the two systems. The system A will have some particular energy, and the system B will have some particular energy, and these two particular energies summed together, that will be that value. Okay, there is no more energy due to interaction. Therefore, whatever may be the distance between the two atoms A and B after that, that doesn't matter, because after that distance, wherever A and B are staying, they have their own energy and they have no interaction in whatever may be the distance. Therefore, the energy will remain a constant. So once the bond is broken, the energy remains a constant like this. Okay, so the curve will be parallel to the u-axis. Okay, so the curve will be like this, and here you can see that there is a minimum, and that minimum corresponds to the minimum energy. This is the minimum. Let me draw it with a yellow color. So this is the minimum, and this minimum corresponds to the minimum energy, right? That minimum energy, and minimum energy means maximum stability, and corresponding to that minimum energy or maximum stability, there is a bond distance. There's a bond distance. This is the bond distance corresponding to the minimum energy or maximum stability. Means when these atoms A and B are placed at this distance from here to here, whatever may be the R value from here to here. When these two atoms are placed at that distance, then the energy of that system will be minimum, or that system is going to be ultra stable, right? And this distance is called the equilibrium bond distance. So this is called equilibrium bond distance, RE, equilibrium bond distance R. So this is that equilibrium bond distance R. This point, whatever may be the value of that point, that is equilibrium bond distance R. So this is from here to here. Okay, equilibrium bond distance R, and the energy corresponding to that equilibrium bond distance RE. Okay, that is the the energy corresponding to that equilibrium bond distance, and then we are considering the energy corresponding to the dissociation. This is the energy corresponding to the dissociation. Okay, energy corresponding to the dissociation. So when the energy is this one, then the molecule reach this one, then the molecule means the molecule is stretched, so that when the energy reaches here, then the molecule will be broken. The molecule will be broken. The bond will be broken. The molecule will separate into two atomic species. Okay, so this energy, the energy corresponding to this one, that is the dissociation energy. Dissociation energy. So what will be the dissociation energy? Dissociation energy is that the energy that we have to supply to the system so that the bond dissociates and the atomic species are formed. So this is the energy corresponding to the equilibrium internuclear distance, right? This is the energy corresponding to the equilibrium internuclear distance. That's the minimum energy. So we have to supply this much energy from here to here, from the equilibrium in the equilibrium internuclear position, whatever may be the energy corresponding to that, plus we have to supply this much energy. So this energy is called equilibrium dissociation energy. Means we are giving an energy from here to here, and that energy is called equilibrium dissociation energy, dE. Okay. So it means that if you are supplying an energy dE to the system, the bond will break. Okay, that is our assumption from this curve. But in fact, if you spectroscopically determine the bond dissociation energy, that bond dissociation energy will be something less than this dE. Okay, or observed bond distance, not bond distance, bond dissociation energy. Observed bond dissociation, we call this as DO, observed bond dissociation energy. That observed bond dissociation energy will be less than the equilibrium bond dissociation energy dE. There is a reason for that. You may be guessing what is the reason. Because here we have found out the energies by fixing the internuclear distance, right? We are fixing the internuclear distance and finding out the energy. But that is not the real case. The equilibrium internuclear the internuclear distance is not fixed really. Rather, The molecule AB is always vibrating. It is vibrating means it is stretching, compressing. Stretching, compressing means the bond distance is elongating, the bond distance is shortening. Elongating, shortening, elongating, shortening, stretching, compressing. Like that, there is a vibratory motion of this. Even if you are placing this molecule at absolute zero, okay, even if you are placing this molecule at absolute zero, even at absolute zero, this molecular vibration will not stop. This molecular vibration will not cease. The molecular vibration is an inherent property of the molecule. This molecule will vibrate always. So, even if you are placing the molecule at absolute zero, this molecule will have some vibrational energy, and that vibration energy, the ground state vibration energy, is half h nu. If you have learned the spectroscopy in the last semester, you already know this. The ground vibration energy is half h nu. So the molecule will have some energy greater than the energy plotted by this curve. Okay, greater than this minimum energy. That energy is half h nu. Half h nu. That is the ground vibration energy. So instead of staying at the value of this curve, instead of staying at the bottom of this curve, the molecule will stay a step above, that is half h nu. That is the ground vibration energy. That energy is already there in the molecule. So when we are supplying the additional energy for the molecule to be dissociated or for the bond to be broken, we don't need to supply half h nu, because half h nu is always already there. So we need to give only extra energy. That extra energy will be from here to here. Okay, so that is less than d. So the extra energy that we have to supply, that is do is less than d. So what will be d? So de will be equal to do plus half h nu. Do plus half h nu, right? Or d is approximately equal to, strictly speaking, d is approximately equal to do plus half h nu. This is what we can understand from here. Okay, see how we have reached so far. We started from a system, and that system have many electrons and many nuclei. And initially we were very confused, because nuclei have their kinetic energy, electrons have their kinetic energy. There are many kinds of potential in the interactions, but we have simplified the system. How did we simplify the system? By just separating the electronic and nuclear kinetic energy terms, right? So we have simplified the system, and the system got simplified by an approximation called Born-Oppenheimer approximation. Born-Oppenheimer approximation. So that is why I told in the beginning itself, this is a very important approximation, and that is going to make your life much simpler. Okay, Born-Oppenheimer approximation. Approximation. Okay, Born-Oppenheimer approximation. Okay, so that is going to make the life of any quantum mechanist much simpler. Otherwise, the life of quantum mechanics would be too terrible, right? Or terrific, or I don't know, whatever. I don't know how to describe that. Okay, and then this Born-Oppenheimer approximation. In the Born-Oppenheimer approximation, what did we do? And they did a mathematical treatment, and that mathematical treatment, they showed that the true molecular wave function is adequately approximated as the true molecular wave function psi, which is in terms of the nuclear position coordinates and electronic position coordinates. Let me write the position coordinate of the electron as QE and the position coordinate of the nucleus as QN. So the true wave function, which is a function of the nuclear and electronic position coordinate, can be approximated as the product of two wave functions, that is psi electronic, which is a function of the electronic coordinates and the nuclear coordinates, into another wave function psi n, that is nuclear wave function, which is only depending upon the coordinate of the nucleus, Qn. Okay, so and so in the Born-Oppenheimer approximation, they did a mathematical treatment to show that the true molecular wave function is adequately approximate like this. Okay, and they also prove that this is true if the mass of the electron divided by mass of the nucleus is raised to mass of the electron divided by mass of the nucleus raised to 1 divided by 4 is very less, very less than 1. Okay, so in Born-Oppenheimer approximation, it introduces a little bit error. You know that any approximation will introduce a little bit error. Here, this approximation will also introduce a little bit error, and this will introduce a little bit error to the ground electronic states of the diatomic molecule. That's why we also consider the diatomic molecule. I gave only approximately. I gave approximate sign here. Okay, I did not equal sign there. Okay, it will anyway. It will bring some error in the ground electronic state of the diatomic molecules. If it is bringing some error in the ground electronic state of the diatomic molecule, it is obvious that the corrections for excited electronic states are much larger. Okay, so it is an approximation method. It is bringing little bit error, but it's okay. Still, it is usually smaller than the errors introduced by other approximations which we are using while solving the Schrodinger equation for many electron molecules. Okay, so that's fine. We have taken a decent approximation. Not we showing the Born and Oppenheimer adopted a decent approximation. So because of that, we will not worry about the corrections, and we will be satisfied with this approximation. And not only we, the quantum chemist, especially will be satisfied by this approximation. So this is one of the very important approximation in quantum chemistry, and this approximation is going to make the treatment of the molecules, many electron many electron molecules, much simpler than we would expect. Okay, so this is what is Born-Oppenheimer approximation, and I hope you understood the essence of the Born-Oppenheimer approximation. If you have any doubt, you can contact me. Either you can contact me email or commenting below, or even you can contact me in WhatsApp. Okay, you can ask more my students. Actually, I am making this video for my own students, but I know that it will leak out to many students. And anyway, you can contact me in any means, anyway, and I will try to answer your questions. Okay, as much as possible. So I hope I did justice to the discussion of Born-Oppenheimer approximation. Thank you for watching.